Our last solids lesson, or our last three-dimensional figure lesson, is about calculating volume, but not through the traditional manner, not actually knowing all the dimensions, not actually plugging it into a formula. We're going to look at two shapes that are similar and use one shape to help us with the other. Our actual objective is to use a scale factor to calculate volume. Now we remember from previous lessons, scale factor is the letter K, and the definition of a scale factor is the ratio of corresponding sides, and that's what we've been using, and that worked great for what we were doing, but not everything has a side. So we're going to change the word side to measure. So a ratio of corresponding measures. Those measures could still be a side, but they could be a height or they could be a radius. Remember that we used the letters A and B, so A came off of one shape and B came off the other, and that showed a correspondence. You may also have seen it as a fraction. Either one of those will work. Remember that similarity is determined by all dimensions having the same scale factor, so it doesn't matter which one I give you, they would all have the same scale factor. So let's look at the progression over time from our previous lessons. Perimeter was in chapter 6, so before Christmas break, and perimeter is one-dimensional. So when we compare the two measures, one from one shape, one from the other, we're going to leave them linear or one-dimensional, so A to B. Area is two-dimensional. We're going to continue to compare our two measures, A to B, but now we're going to square them as area is squared, or two-dimensional. Volume is three-dimensional. We are going to continue with our comparison of A to B of our two measures, one from one shape, one from the similar shape. But this time, because volume is three-dimensional, we're going to cube those. So perimeter is A to B, area is A squared to B squared, and volume is A cubed to B cubed. Let's do some basic skills first. What is the ratio of their volumes, and they being, in this case, cubes? The ratio of the sides of two similar cubes is 3 to 5. We know that our A is 3 and our B is 5. We want to do the volume, so we need to cube each of those. So 3 cubed to 5 cubed. So 3 cubed is 3 times 3 times 3, which is 27. And 5 cubed is 5 times 5 times 5, which is 125. So our scale factor for their volumes would be 27 to 125. Number 2, the ratio of the diameters of two similar cones is 1 to 6. So again, yeah, they're cones, and yes, they're going to have heights, but we don't need to mention them because the ratio of heights would also be 1 to 6. Again, this is my A, this is my B. So I need to cube them to do my volumes. 1 times 1 times 1 is 1. 6 times 6 times 6 is 216. So 1 to 216. So that's how the volumes would compare. The volume of the second cone would be 216 times bigger than the volume of the original cone. So that leads us into our second set of examples. The solid is similar to a larger solid with the given scale factor. Find the volume of the larger solid. So they've just shown us a picture of one of them. They're saying somewhere else there's an even larger sphere, and we want to find the volume of this larger sphere because we don't know it. We do know the volume of the smaller sphere is 118 pi. We also know that the scale factor is 7 to 6. So we currently know A to B is 7 to 6. Our question's all about the volume, not the linear measurement. So I am going to need to cube both of those. So 7 cubed is 343, and 6 cubed is 216. So 334 to 216 is how the volumes compare if you don't know them. Now we do actually know the volumes. Now we have to be really, really careful. It says 7 to 6, so it makes it seem like this should be your 7 and this should be your 6. But remember, this one's larger. This one's your 7, this one's your 6. So 7 cubed is 343, so the volume that goes with that is the mystery volume. 216 is the volume of the smaller one, and the volume that goes with that is 118 pi. So the only thing about that 118 pi is it's actually allowing us to not have to multiply by 3.14. So we just want to be real careful about how we do this. So I'm going to totally ignore the pi when I cross multiply. When I cross multiply, I'm only doing 343 times 118. So that's 40,474, and then there's a pi equals 216 times the volume. Again, I'm going to ignore the pi. I'm just going to divide by the 216. So I'm going to get 187. Now I'm going to round it to 0.38. So what happens to the pi? Well, I've just been carting along, so I just keep carting it along. So the volume of the larger one is 187.38 pi inches cubed. So that's the volume of my larger one. Now we have a pyramid. Again, this pyramid, pretend I can draw because we all know that I can't, has a larger one somewhere over here. 2 to 5. Oh, so this is in the order that we want. This is a 2 and this is a 5. Now, we don't know if it's the side length or the height or even the slant height. We don't care because they would all be 2 to 5. We know the volume of this one is 400 cubic inches. We do not know the volume of this one. So let's start with our scale factor, 2 to 5. We're going to cube it because we want volume. So 8 to 125. So 8 to 125 would be the volumes after you reduce them. But right now we don't know them, so we can't really reduce them. So we're going to get one. So with the 8 is a 400, and with the 125 is the volume we don't know. So we're going to cross multiply. So 8 times V equals 125 times 400, which is 50,000. Divide by 8, and our mystery volume, the volume of this larger pyramid, is 6,250 inches cubed. We took our basic skill and converted a standard scale factor to a volume scale factor by cubing it. We just need to be very careful that the volume they gave us is the smaller one. So the volume they gave us in the proportion has to go with the smaller value. That volume they gave us has to go with the smaller value. Then we cross multiply and divide. If you have a pi symbol, don't worry about it, just cart it along, it'll be part of your answer.